What if the strangest star in our galaxy was staring at us the entire time, and we almost missed it? Somewhere out there, roughly 1,500 light-years from Earth, a star behaves in a way that no other normal star behaves. It dims, suddenly, and without warning. Sometimes by 1%. Sometimes by 22%. It fades slowly over decades, then it brightens again, as if something enormous is moving in front of it, blocking its light, and then, letting it go. For almost a decade, some of the smartest astronomers on this planet could not explain it. And for a brief, electrifying moment in scientific history, one of the theories on the table was almost too strange to say out loud. What if it isn't dust? What if it isn't comets? What if it's a structure? Something built. Something artificial. Something that shouldn't exist, but does. This is not fiction. This is not clickbait dressed up as science. This is one of the most well-documented mysteries in modern astrophysics, and it connects to something even bigger, a live, ongoing search happening right now, in 2026, for real infrared signatures that could indicate advanced civilizations harvesting energy directly from their stars. Today, we are going to walk through it properly. We're going to talk about vanishing light, about planets being slowly devoured by their own suns, about the scientific arguments that ruled out the easy explanations, and about the megastructure hypothesis that refused to fully die, even after most of it was debunked. Stay with me, because by the end of this, you're going to look at the night sky differently. Let's start at the beginning. In 2009, NASA launched a spacecraft called Kepler. Its job was almost embarrassingly simple on paper. Stare at roughly 150,000 stars, for years, without blinking, and watch for tiny dips in their brightness. Because when a planet passes in front of its star, from our point of view, it blocks a small, predictable, repeating sliver of light. That's how Kepler found thousands of exoplanets. Regular dips. Regular rhythms. Predictable orbits, like clockwork. And then, in 2015, a group of citizen scientists working on a project called Planet Hunters found something that didn't fit the pattern at all. The star was catalogued as KIC 8462852. Most people just call it Tabby's star now, named after the astrophysicist who led the investigation, Tabitha Boyajian of Louisiana State University. And what Boyajian and her team found in the data was, frankly, bizarre. Instead of small, clean, repeating dips like a planet would cause, Tabby's star showed deep, irregular, chaotic dimming events. Sometimes the light dropped by 15 to 20%, for days at a time. For context, even a planet the size of Jupiter passing in front of a sun-like star only blocks about 1% of its light. 20% is not a planet. 20% is something enormous, or something very close to the star, or something we had never accounted for in our models at all. It got stranger. A year later, in 2016, another LSU astronomer named Bradley Schaefer went digging through more than a century of archived photographic plates of the sky. And he found that Tabby's star had also been fading, slowly, steadily, over the long term. By his estimate, the star had dimmed by roughly 14% between 1890 and 1989. That's not a week-long dip. That's a century-long decline in the light output of a single, otherwise unremarkable star. So now scientists had two mysteries stacked on top of each other. Sudden, dramatic, short-term dips, and a slow, long-term fade that shouldn't be happening to a mature, stable star at all. Naturally, the internet noticed. And naturally, the theories multiplied fast. Some suggested a cloud of shattered comet fragments, crossing the star's path in an unusual orbit. Others proposed a recent planetary collision, kicking up a massive amount of debris. A few papers explored the idea of a disrupted moon, breaking apart and scattering material around the star like a dusty veil. And then, in late 2015, a Penn State astronomer named Jason Wright, along with his colleagues, published something that made headlines around the world. They pointed out that the light curve of Tabby's star was consistent, at least statistically, with what you might expect from a swarm of enormous artificial structures, built to capture a star's energy. This idea has a name. It's called a Dyson sphere, or more realistically, a Dyson swarm, first proposed by physicist Freeman Dyson back in 1960. The concept is almost elegant in its logic. A sufficiently advanced civilization would eventually run out of energy on its home planet. So the next logical step, if you're thinking on a truly cosmic timescale, is to build structures, satellites, solar collectors, orbiting platforms, that surround your star and harvest its output directly. Not science fiction for its own sake. An engineering solution to a resource problem, scaled up to a stellar level. Wright wasn't claiming Tabby's star definitely had aliens around it. He was careful, methodical, and scientifically responsible about it. What he said, essentially, was this: we cannot rule it out yet, and it is a hypothesis worth testing, because the data genuinely doesn't fit anything we've seen before. And that's the part that made this so gripping. This wasn't some fringe blogger making a wild claim. This was a peer-reviewed conversation, happening inside real astrophysics journals, involving real telescopes, real data, and real scientists who were being intellectually honest about the limits of their own explanations. The public reaction was so intense that in 2016, Boyajian and her team actually launched a Kickstarter campaign, asking the public to help fund dedicated telescope time to monitor the star continuously, so that the moment it started dimming again, professional observatories around the world could turn their instruments toward it in real time, rather than finding out weeks later from archived data. The campaign raised well over its goal, which tells you something about how deeply this mystery had captured public imagination, scientists and enthusiasts alike, all wanting the same thing. Answers, in real time, as they happened. So the next question became obvious. If this really was a megastructure, how would we even prove it? The answer scientists landed on was infrared radiation. Here's the logic. If Tabby's star were surrounded by a natural cloud of dust or debris, that material would absorb starlight and then re-emit it as heat, specifically in the infrared part of the spectrum. Same thing if it were an artificial structure. Any object, dust cloud or Dyson swarm, that blocks visible light from a star has to do something with the energy it absorbs. It doesn't just vanish. By the laws of thermodynamics, it gets re-radiated as infrared heat. So NASA turned its infrared eyes toward the star. The Spitzer Space Telescope, and later the Swift mission, both scanned Tabby's star, hunting for that telltale thermal glow. And this is where the plot thickens even further, because the results were confusing in their own right. If it had been a storm of comets, as one early theory suggested, astronomers expected to see a very specific level of infrared excess from all that vaporizing ice and rock. They didn't find nearly enough of it. The comet swarm theory started looking shakier by the year. For a while, this absence of a clean infrared signature actually kept the megastructure hypothesis technically alive. No excess heat that clearly pointed to ordinary dust, meant scientists still couldn't fully close the door on stranger explanations. But science doesn't stay static, and neither did the investigation into Tabby's star. Between 2017 and 2019, a wave of new studies started narrowing things down. Researchers used ground-based observatories, citizen astronomer networks, and archived Spitzer and Swift data to study exactly how the star dimmed at different wavelengths of light. And they found something crucial. When Tabby's star dipped, it dimmed more strongly in blue light than in red or infrared light. That detail matters enormously. A large, solid, opaque object, like a megastructure, or a planet, blocks all wavelengths of light more or less equally, because it's just a solid shape passing in front of the star. But fine dust particles behave differently. Small dust grains scatter blue light more efficiently than red light. So if the dimming shows a strong color dependence, favoring blue light being blocked more than red, that's a very strong fingerprint of dust, not a solid structure. That's exactly what the data showed. By 2019, using combined data from Spitzer, Swift, and even a ground-based observatory in Belgium called Axiverse, NASA researchers concluded that the most likely explanation for the long-term dimming of Tabby's star was an uneven ring, or a lopsided cloud, of ordinary dust, orbiting the star. Not comet debris in the classic sense. Not an alien megastructure. Just dust, but distributed in a strange, clumpy, asymmetric pattern that made the star's light curve behave in ways nobody had modeled before. Now, I want to be honest with you here, because that's the whole point of this video. Some corners of the internet like to frame this as, quote, scientists proved it wasn't aliens, end quote, like the mystery is fully closed and boring now. That's not quite accurate either. What actually happened is more interesting than that. The short-term, deep-dimming events, the sudden 20% drops, are now reasonably well explained by clumps of dust, possibly from a disrupted exomoon or shattered planetary body, orbiting unevenly around the star. But researchers have openly acknowledged that some aspects of Tabby's star's behavior, including certain asymmetries in the dimming and its overall unusual history, still don't have a complete, universally agreed-upon explanation. The dust hypothesis is the leading one. It is not, technically, the final word on every single detail. And here's the thing that I think gets lost the most in all of this. Even though dust explains most of what we now know about Tabby's star specifically, the megastructure hypothesis itself did not go away. It didn't die with this one star. It evolved into something much bigger. It became an actual, structured, ongoing search. Which brings us to the second half of this story, and honestly, the part that I think is even wilder, because it's happening right now. Before we go further, let's talk about a completely different kind of vanishing act. Not a star fading. A planet dying. Roughly 600 light-years away, in the constellation Auriga, there's a planet called WASP 12b. It's a gas giant, about 1.5 times the mass of Jupiter, and it orbits its star so closely that a full year on that planet lasts just over 1 day. 1 day. Its daylight side gets baked to temperatures of roughly 2,500 degrees Celsius. That's hot enough to vaporize rock. Since its discovery in 2008, astronomers have been tracking WASP 12b's orbit with extreme precision, timing exactly when it passes in front of its star. And what they found, confirmed through years of data collected by the Spitzer Space Telescope and refined by a Princeton-led team of astrophysicists in 2019, is that the planet's orbit is measurably shrinking. Not by a lot each year. About 29 milliseconds sooner, every single year. But that number compounds. According to the research, led by astrophysicist Samuel Yee and his colleagues, WASP 12b is spiraling inward, and it will be completely consumed by its own star in roughly 3 million years. In cosmic terms, that's practically tomorrow. But orbital decay isn't the only way a planet can physically come apart, close to its star. There's another real, observed process, called atmospheric stripping, and the first planet ever caught doing it, in dramatic fashion, is a hot Jupiter called HD 209458b, nicknamed Osiris. Back in 2003, using the Hubble Space Telescope, an international team led by Alfred Vidal-Magyar of the Institut d'Astrophysique de Paris made history. For the first time, astronomers directly observed the atmosphere of a planet outside our solar system, evaporating. Not metaphorically. Literally boiling away into space. HD 209458b orbits its star from a distance of only about 4 million miles, closer than Mercury is to our Sun, completing a full orbit in just 3.5 days. The heat is so extreme that the planet's hydrogen atmosphere puffs up, escapes the planet's gravity, and streams away behind it, forming a vast, glowing tail, stretching more than 120,000 miles long. Astronomers said it looked remarkably like a comet. Researchers estimated the planet was losing at least 10,000 tons of hydrogen gas every single second. Follow-up observations later even detected oxygen and carbon being swept away in that same outflow, evidence that the evaporation was pulling material from deep within the planet's atmosphere, not just its outer edge. Scientists have since proposed that planets like this, hot Jupiters sitting close enough to their stars for long enough, could theoretically be stripped down entirely over time, left as bare, rocky cores where a gas giant's atmosphere used to be. It's a real, physically measured, mathematically modeled process, and it gives us a second, completely natural way that a planet's presence around a star can fundamentally, dramatically change, without needing a single unexplained force. This is what real orbital decay, and real atmospheric loss, look like. Not a mysterious disappearance from our telescopes overnight, but a slow, physically explainable, gravitationally inevitable death spiral, caused by tidal forces between the planet and its star. The star's gravity is literally stealing energy from the planet's orbit, dragging it closer, year after year, until eventually, it will fall in and be destroyed. Why does this matter for our bigger story? Because it shows us something important. When astronomers claim a planet is being destroyed, or an object's behavior is unexplainable, they don't just guess. They measure. They track. They collect years, sometimes decades, of precise timing data, and they publish it for other scientists to challenge and verify. Real astronomical mysteries get solved, or at least seriously investigated, through relentless, boring, meticulous observation. But orbital decay isn't the only way a planet can seem to vanish. There is one case, a genuinely famous one, where a confirmed exoplanet did exactly what our title describes. It was there. Astronomers photographed it. NASA announced it to the world. And then, years later, it was gone. Its name was Fomalhaut b, and its story is one of the strangest in the history of exoplanet science. In 2008, NASA announced something extraordinary. Using the Hubble Space Telescope, astronomers had directly photographed a planet orbiting the bright, nearby star Fomalhaut, located just 25 light-years from Earth. This wasn't a shadow, or a shift in starlight, or an indirect wobble in a star's motion. This was an actual, visible dot of light, captured in visible wavelengths, moving exactly the way a planet should move. It was hailed, at the time, as one of the first exoplanets ever directly imaged. Follow-up observations in 2006 confirmed the object was still there, still moving, still behaving like a world in orbit. For years, Fomalhaut b sat in the record books as one of astronomy's great visual triumphs, actual photographic proof that we could see another planet with our own eyes, from 25 light-years away. Then researchers went back to check on it, using every scrap of archival Hubble data they could find. And in 2014, when they looked again, it simply wasn't there anymore. Not dimmer. Not partially obscured. Gone. Vanished from the images entirely, in a location where a real planet, following a real, stable orbit, absolutely should have still been visible. Astronomers Andres Gasper and George Rica, at the University of Arizona, spent years reanalyzing every available observation of the Fomalhaut system, and in 2020, they published their conclusion in the Proceedings of the National Academy of Sciences. Their finding was almost poetic in how strange it was. Fomalhaut b, they argued, was never a planet at all. It was something else entirely. An enormous, expanding cloud of fine dust, most likely the debris from a violent, high-speed collision between two icy, planet-forming bodies, each roughly 125 miles across, smashing into each other in the star's outer debris ring, sometime shortly before Hubble's first image in 2004. In other words, we hadn't been watching a planet at all. We'd been watching the glowing wreckage of a cosmic car crash, still hot and bright when Hubble first caught it, and then slowly thinning out, expanding, and fading into invisibility over the following decade, exactly the way a dust cloud would, and exactly the way a solid planet never could. Gasper summarized it best in NASA's own release on the discovery. In his words, Fomalhaut b was doing things a real planet should never do. It was fading. It was expanding. And based on its measured trajectory, it appeared to be drifting on a path that would eventually let it escape the star's gravity entirely, something only possible for an object with essentially no mass, like a dust cloud, and completely impossible for an actual planet. And remarkably, this story didn't end there either. Newer Hubble observations, published in December of 2025, caught what appears to be a fresh version of the exact same event happening again, in the very same debris ring around Fomalhaut. A new expanding blob of dust, matching the size and behavior expected from another planetesimal collision, giving astronomers, for the first time, something close to a live look at the kind of violent impact that likely created Fomalhaut B in the first place. According to Jason Wang, an astronomer at Northwestern University involved in the new research, it's the first time scientists have ever directly observed colliding planet-building blocks outside our own solar system. So there it is. A real, documented, thoroughly verified case of a confirmed exoplanet disappearing from our telescopes. It happened. It's in NASA's own archives. But the explanation wasn't a hidden megastructure, or some unexplainable act of cosmic sabotage. It was something almost as dramatic in its own right, a titanic collision between worlds still being born, caught by accident, 25 light-years away. And that brings us right back to the biggest, boldest question in this entire story. If megastructures are a real hypothesis worth testing, has anyone actually gone looking for them, systematically, across the galaxy? The answer is yes. And it's happening in the years right around us. In 2022, a team of Swedish researchers, led by astronomer Mattias Suazo at Uppsala University, launched something called Project Hephaistos. Their goal was ambitious, and refreshingly direct. Search an enormous dataset of millions of stars, using data from the European Gaia satellite, the 2-micron all-sky survey, and NASA's WISE infrared telescope, and look for stars that have an unusual excess of infrared light, exactly the kind of thermal signature you'd expect from a partial Dyson sphere. Their first paper, published in 2022, didn't find any strong candidates, but it did something valuable. It set an upper limit on how common partial Dyson spheres could possibly be in our galaxy, and it built the framework, the actual search methodology, for finding them. Then, in May of 2024, Project Hephaistos published its second paper, and this time, the results were genuinely startling. Out of roughly 5 million stars analyzed, the team identified 7 candidate stars, all of them small red dwarfs, all showing a strange excess of mid-infrared light, at temperatures between 100 and 300 Kelvin. That temperature range is important, because it's exactly the thermal signature predicted by theoretical models of partial Dyson spheres, structures that don't fully enclose a star, but capture a significant portion of its energy output. For a moment, the scientific world had 7 real, data-backed, mathematically consistent Dyson sphere candidates. Not myths. Not speculation and internet rumors. Actual coordinates, actual stars, actual anomalous data sitting in professional astronomical catalogs, waiting to be explained. But, and this is the part that real science always insists on, a candidate is not a confirmation. So the follow-up investigations began immediately. Researchers cross-referenced the 7 candidate stars against archival radio survey data, because if these signals were coming from background objects instead of the stars themselves, that would explain the anomaly without needing anything artificial at all. And by late 2024, using observations from radio telescope networks like the Enhanced Multi-Element Radio-Linked Interferometer Network, researchers found that at least 2, and later 3, of the 7 candidates had offset radio counterparts. In simple terms, some of that strange infrared light wasn't coming from the star at all. It was coming from something behind it, in the same line of sight, most likely a distant, extremely luminous background galaxy, the kind astronomers call a hot dog, short for hot dust-obscured galaxy. That's a genuinely elegant, unglamorous, but scientifically satisfying explanation. Space is deep. When you're staring through millions of stars, sometimes a background object lines up almost perfectly with a foreground star, and its light gets blended together, creating a false signal that looks anomalous, but isn't. Statistical modeling published later in 2024 estimated that the known surface density of these hot dust-obscured galaxies was actually high enough, mathematically, to potentially account for all 7 of the original candidates being chance alignments, rather than genuine anomalies around the stars themselves. So, is the mystery solved? Case closed, nothing to see here. Not entirely, and this is where I want you to really pay attention, because this is the current, live state of the search, as of 2026. In the summer of 2025, the James Webb Space Telescope, the most powerful infrared observatory ever built, was pointed directly at 2 of the remaining unexplained Dyson sphere candidates, known in the research as candidates D and E, the two that had shown no radio counterparts at all in earlier surveys. Webb's extraordinary resolution allowed astronomers to do something no previous telescope could: separate the light of the candidate star from any faint background object sitting almost directly behind it. The results, published in mid-2026, found that the infrared excess in these remaining cases also appeared to be dominated by contamination from background sources, rather than from the stars themselves, or from any hypothetical structure surrounding them. Follow-up work using deeper near-infrared imaging and precise position measurements in 2026 continued to chip away at the number of truly unexplained candidates. In other words, one by one, the 7 original Dyson sphere candidates from Project Hephaistos have been, or are actively being, explained away through ordinary, if statistically unlucky, astrophysical contamination. Background galaxies, misaligned in our line of sight, mimicking the exact thermal signature scientists were trained to look for. But here's the honest, important caveat, the one that keeps this story genuinely open instead of neatly wrapped up in a bow. As of the most recent published research, not every single candidate has been fully and conclusively resolved. A handful still sit in a kind of scientific limbo, awaiting deeper observations, better resolution, and more data, before anyone can say with total certainty exactly what's producing their unusual light. The searching hasn't stopped. If anything, Project Hephaistos and the researchers who followed up on it have built an entire methodology, a genuine, repeatable, falsifiable scientific process, for hunting technosignatures hidden in plain sight, inside data we already collected for completely different reasons. So let's step back, and put all of this together. We started with a star that shouldn't dim the way it dims, discovered almost by accident by citizen scientists sorting through Kepler data. We followed real astrophysicists as they proposed, tested, and mostly ruled out an artificial explanation, replacing it with an equally strange, but naturally occurring, uneven cloud of dust. We looked at a planet, WASP 12b, genuinely being consumed by its own star, not through some unexplained vanishing act, but through the slow, measurable, gravitationally certain process of orbital decay. And we followed a real, ongoing, peer-reviewed search for Dyson spheres across millions of stars, a search that found 7 tantalizing candidates, and has spent the years since carefully, rigorously, working to explain, or fail to explain, every single one of them. None of this required exaggeration. None of it required inventing a phenomenon that doesn't exist. The real story, the true one, backed by actual telescopes, actual published papers, and actual scientists willing to say, honestly, we don't fully know yet, is more compelling than any fictional version could ever be. Because here's the truth about how science like this actually works. It's not about telescopes suddenly finding nothing where something used to be. It's not about planets cleanly vanishing overnight without a trace, as if the universe erased them. Real astronomical mysteries are messier than that, and slower than that, and far more human than that. They involve years of data. They involve wrong turns, and half-right hypotheses, and stubborn anomalies that refuse to fit neatly into any box. They involve scientists who are willing to say the word alien out loud, in a serious academic paper, not because they believe it, necessarily, but because intellectual honesty demands that you test every explanation the data can support, even the uncomfortable ones. And maybe that's the real takeaway here. Not that aliens are hiding around a red dwarf star 300 parsecs away. We genuinely don't know that, and as of right now, the evidence is leaning heavily against it, star by star, candidate by candidate. The real takeaway is this. Somewhere in a dataset sitting on a server right now, there might already be the first hint of the strangest discovery in human history, and we might not recognize it yet, buried under thousands of ordinary explanations, waiting for the right scientist, the right telescope, or the right follow-up observation, to finally pull it into focus. So the next time you look up at the night sky, and you see a star quietly holding its light steady, remember, some of them don't behave that way. Some of them dim, unpredictably, for reasons we're still working out. Some of them are getting slowly devoured by their own gravity. And a small, carefully checked handful of them, are still, technically, unexplained. We are not watching planets disappear from our telescopes without explanation. We are watching something arguably more fascinating. Real scientists, in real time, chasing down real anomalies, refusing to accept easy answers, methodically closing the gap between mystery and understanding, one star at a time. Think about what that actually means, for a second. A dot of light that NASA proudly announced as a planet in 2008 turned out, by 2020, to be the smoking wreckage of a collision nobody witnessed. A star that seemed to defy every known model of stellar behavior turned out to be wrapped in an uneven, invisible ring of dust, kicked up by some event we still don't fully understand. A gas giant 600 light-years away is right now, as you listen to this, measurably spiraling closer to its own destruction, 3 million years from a fiery ending that astronomers can already predict with real data. And 7 stars, flagged by a rigorous, methodical search for alien engineering, are still, one by one, being checked, cross-referenced, and re-observed with the most powerful infrared telescope humanity has ever built. None of that needed to be exaggerated to be extraordinary. That's the part worth sitting with. And until every one of those remaining anomalies is fully resolved, the question stays open. What else is out there, hiding in the light we've already collected, waiting for someone to finally notice? If this kind of deep space mystery fascinates you as much as it fascinates me, make sure you're subscribed, because we are only just getting started uncovering the strangest, best documented anomalies in modern astronomy.